The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone. Before we get started, I just wanted to make sure that everyone can hear us clearly. If you can hear me now, if you would please just send a comment in there in the questions section and let us know if you can hear us and how well.
Okay, well, I guess we're going to go ahead and get started. Seems like everybody can hear us. So first off, just wanted to welcome everybody today. Do a couple quick introductions, and then we will get started with the program. Very quickly, my name is Chris Fay. I'm the Vice President of TPM. And then on the line here, we also have Dustin Manning. He's one of our application engineers working out of our Charlotte office. And so today we're going to go through basically the fundamentals and some of the processes around laser scanning specific to the AEC and manufacturing industry, and then also take an opportunity to take a look at some of the technology and the software, and then review some applications. So I just want to take 2 seconds and just make sure we introduce who TPM is and what we're all about. So this will probably take a minute, and then we will start with the details of the program. So we're a technology company. We were founded in 1973. Have nearly 100 employees, and really focused on the Carolinas and parts of North Georgia are the areas that we serve. We have 5 offices. Our headquarters is in Greenville, South Carolina. We have offices in Columbia and Charleston, South Carolina, and also have offices in Charlotte and Raleigh, North Carolina. Our business serves over 3,000 customers each year, and you know, we're really a solutions-based organization with a number of different legs. The way that our business is really broken up is into 4 strategic divisions. About half of our business really revolves around the engineering and design space. So our architecture, engineering, and construction division is focused primarily on Autodesk solutions, consulting services around those solutions, and also this is where our laser scanning business lies. Our manufacturing business really is focused on 3D CAD and simulation tools, 3D laser scanning, 3D printing solutions, and really the bulk of our business is geared towards the design and engineering community. We also have 2 supporting divisions, our document and print solutions. This is document management software, engineering plotters, office copiers, and a number of workflow automation tools that we bring to our engineering customers. And then we also have another business called the Color Lab, large format trade show displays, presentation graphics, office murals, etc. So very diverse business, again, really honed in and focused here in the Carolinas and the Southeast. And I think with that, I'm gonna thank you guys for attending. Dustin's going to take us through the presentation. I know that Dustin wants this to be an interactive presentation, so if you have questions, please feel free to enter those into your to the dialog box, and we'll address those, and certainly we'll open up for even further questions at the end. So with that, Dustin, I'm going to hand it off to you, buddy, and thank you guys for attending.
All right, well, thank you all. We have a nice turnout here for our webinar today, and TPM is really excited about technology, and I'm excited about 3D scanning. Every time we have a conversation about 3D scanning, someone else comes up with a new application. All kinds of interesting things going on in the world. If you follow anyone in 3D scanning on LinkedIn or follow any blogs or anything, it's just amazing what people are coming up with. And so today we're going to talk about the fundamentals of 3D scanning. So it's going to be a fairly technical talk, making sure we understand how the technology works in different applications. So exactly what is this? What is 3D scanning? We're talking about non-contact measurement. Faro, which is a company we're partnered with, is known for 3D measurements. So there's different parts like their arms, so contact measurement that measures at very high precisions, so into thousandths of inch. And we're talking about the 3D scanner shown there on the left, the Focus 3D, and it is non-contact, and it is high accuracy, although it's not thousandths of an inch. We are talking about millimeters. So this is a perfect application for piping, architecture, historic preservation, anything that would work in the realm of millimeters. This is a line of sight instrument. So just like our eyes work, the instrument will do the same thing. And so you'll see how that affects the workflow and the other requirements that come with working with this kind of instrument. So as I said, when we're talking about the hardware in this webinar today, we're going to be focused on this scanner specifically. This specific one is about 2 years old, and it's really taken the market by storm. It's filled in a lot of the technological gaps that we had before the scanner came out. So limitations in the type of atmosphere and environment that we can scan in. This scanner really shines. So first off, safety. It's a class 1 laser, so we don't have to worry about damaging your eyes or being in any sensitive areas there. This model, the X330, so the 330 stands for meters. It works in about a 1,000-foot radius. So when you think about range, this is incredibly powerful. Before this model was released, we were, for the most part, limited to working in less than half that range. And so the accuracy here, we're looking at plus or minus 2 millimeters inside of that 1,000-foot radius. So we're talking about 1/8 of an inch. So from each scanner position, we can see in a 360-degree horizontal and vertically 300 degrees. So the only thing that we're not seeing is just what's directly below the scanner, so we're basically not scanning the tripod each time. This is GPS enabled, so if we're outside and we have a good signal, we will at least have some idea where we are geolocated. And this is equivalent to what's in your phone, so it's not a survey-grade GPS, but it does assist in the process of taking multiple scans and registering them together. We also have Wi-Fi, and this enables us to remotely control the scanner. So if we had to place it in a place that wasn't so convenient to touch the screen, then we could connect with a laptop or a tablet and start the scan from a remote location. We could also download files, so it's very convenient. All right, the Faro is very, very compact. It's about half the size of most other scanners and about half the weight. So it's easy to take this on a plane if you're going off-site. It comes in a nice Pelican case, and there's also options for things like a backpack to make it even more portable. It also has a built-in camera, so we're able to get color photography along with our scan data, and you'll see this later in the presentation where we have a full 360-degree panoramic color image to go along with all that other data. Most hardware and software has come a very long way in the past couple of years. Batteries are the same. We can take scan after scan, and I've got all the way up to 5 hours of battery life using this scanner. If there's extreme conditions, of course, it always affects battery life if it's very hot or very cold. And all the accuracy measurements are certified by NST and ASTM. The Faro is fantastic with the interface. If you can operate a smartphone, this is probably even simpler. There's a few settings that determine the density of the point cloud that we're collecting, and the settings for photography. The file management is very simple. So when you're talking about getting started with 3D scanning, you're not looking at a lot of time to understand a complicated piece of hardware. Most people feel comfortable operating it after about a day. Also the training that comes along with this, that's performed by Faro, is a wonderful experience. Very great trainers over at Faro. All right, a little bit more. So not just the Faro Focus 3D, but 3D laser scanners in general work in complete darkness. Okay, so this is a laser. So if we were to set the scanner up into a completely dark room, the laser would self-illuminate. So to give you an idea here, let's take a look at this data set, and this is just a screenshot out of Autodesk's Recap software. And it's kind of hard to get a sense of scale in this, but this is the Tuckaleechee Caverns in Townsend, Tennessee. And the back stalagmite there is about, let's see, about 20 feet tall. So there's a very large expanse in here, and there was only about 3 or 4 100-watt or so flood lamps in there. So just enough light to see to walk around safely, but when it comes to photography, there was very little light there, and the laser performed flawlessly. I never get tired of looking at this data. I think it's fantastic. You can see the coloring here that we're seeing is just based off of elevation. So the lower elevations are the darker orange, and the taller spots are closer to white. So we're not looking at any photography in this case. All right. So the scanner works very well also in bright conditions. Previously in other models, there were issues when trying to scan in very bright conditions. So if you were scanning in the middle of the day, the quality of the scan and the photography would be, not the best. But Faro's made great advancements with their laser technology, and it really shows off. In this next screenshot, you'll see the Giordano Velodrome in Rock Hill, South Carolina, and this was taken around 1 o'clock in the afternoon. It was in the middle of summer. It was incredibly bright, but the quality of the laser scan data was great, and then you can see just how vivid the imagery is that comes from the photography. Okay, so once we scan, what do we end up with? What exactly are we getting when we download the files from the scanner? Firstly, we have a Grayscale point cloud, and the point cloud, a big buzzword, but it's really not all that complicated. It's essentially a series of X, Y, and Z values along with reflectivity. So just a big coordinate system along a long list of points measured in 3D space. And here we'll see the upper circle there. Along this ducting, you'll see the other values in the bottom right. So you'll see the XYZ coordinates, and then the RF value down there is reflectivity. So what we're looking at is it's in a very dark area. There's very little lighting here. And that's a highly reflective surface. And I was trying to remember exactly what it looked like in person, but it's something like foil. And you can see that the scanner does a very good job of capturing even highly reflective surfaces like that. The nature of laser scanning is that if something is too highly reflective, then it can't capture that information. So if we're looking at scanning a mirror, we're not going to get very useful data because it's just too reflective. And so you can see from this scan, we have a lot of information there. You can see all the conduits, all the different electrical panels and whatnot. And what's so great about 3D scanning, I'm always surprised at how much data we can pick up from just one location. I mean, it is line of sight, obviously, so there's always going to be limitations of what you can see around. But if you set up near a window and you're just concerned about what's on the interior space, when you go and look at your scan in the software, you'll realize that you were scanning out the window and you were picking up data a quarter of a mile away. All right. So we mentioned the photography side of this. We have that 70 megapixel camera that captures the 360-degree view after the scanner picks up the point cloud. So the photographs alone are very useful. We were just speaking with an architect yesterday that found so much use in the panoramic images that they felt more inclined to use that for communication purposes internally and to clients and whatnot. And here's an example of a point cloud. So keep in mind this is not a photograph that we're looking at here. All right. So on the right third, you'll see that it's just grayscale. So that's just the point cloud data there. And on the left 2/3, we have the colorized point cloud. So the scanner first collects all of the 3D point information, and then it takes another pass and collects all of the photography. And the software that we'll look at, so mainly Ferrocene or Autodesk Recap, inside the software it takes all of the information of the photography and overlays the color imagery onto the point cloud. All right. In the screenshot, you can see, and I'll make a little marker here. So that was the location of one of the scans. It's a little 3D model of the scanner itself. And one thing you'll notice, the closer you are to the scanner, the higher the density of the points. The nature of laser scanning is that we're mostly concerned about density. When we talk about resolution or quality and things like that, we're talking about the spacing between each point. And the closer the objects are to the scanner, the higher the density of the points. And if you look over to the left, you'll see the further we go out, the higher that spacing is. So the technology, like I said, it's very simplistic as far as you make a couple of settings. You determine where you want to scan just based on your area of interest. If you were going to scan some pipe, you only need to see a portion of that pipe to actually be able to place it into 3D space and to use it for an as-built drawing or something like that. But since it is a line of sight instrument, we do have to make plans on traversing around objects and then tying those objects together, or rather those scans together, to create a complete picture. All right. The process of taking multiple scans and relating them to each other is called registration. The hardware is an amazing measurement device, but there's one thing that it doesn't do, and it doesn't really know where it is. When it takes the scan, everything is going to be related to the position of the scanner. So that's your origin, and from there it's just measurements. So we have to use software to tie all of these different scans together and build the complete picture of our area of interest. Okay. In this image here, you can tell it's a little bit confusing, right? We have about 7 scans, and each color represents a scan location. And here, the scanners, and now let me back up just a little bit. This is an outdoor scan, so if I wanted to, I could have had the GPS turned on, but for demonstration purposes, I wanted to show you how the scanner works and how much information is there. So without GPS information, we have no idea where these scans are taken in the world. So when we bring them into the software, all we see is a jumbled mess because all of the scans happen from that origin of 0. Once the process of registration has taken place and everything is in order, we'll have something that makes a whole lot more sense. So now you see all those same colors, and they're all related to each other. All right, so this is a picture actually of the point cloud from the Shelby Airport in North Carolina. I think it was Shelby. So each one of these scans you can see has a label. So we have number 1 through, and yeah, there were 7, and again each color corresponds to a specific scan. And what we're concerned about when we're scanning, the whole theory behind scanning and where we place it and how many scans we take, is really commonalities. All right, for the software to be able to do its job, which is really amazing at the job, it's the algorithms that they use to to bring all this point cloud data together it's pretty fascinating. You'll see here the commonalities that we're looking for can happen in a few different ways. All right, the first option and was really the standard operation was to use targets. That's it. So just like in traditional survey methods, we have to have known points in space to be able to relate objects to one another. And in 3D scanning, there are two ways we can use targets. These are not the only ones, but the most common. And you'll see spheres and checkerboards. And what we want is to place these spheres in a place that the scanner can see them and get enough points of measurement on them so that when those same objects are seen from another location, they're able to relate those to each other and place them in relationship in 3D space. All right, so the spheres come in multiple sizes. Small and common size are somewhere around a 5-inch diameter. The spheres are useful because you can see them from multiple angles, and the checkerboards are something that have to be rotated and turned so that they're visible from different points of view. In this screenshot, you can see this was a scan or several scans taken outdoors, and we were using a targeting method to register these scans together. The software understands the relationship between all of these spheres, and so it's able to intelligently tell one from the other and then give them common names from scan to scan. The spheres are automatically detected, so the software understands how to go and look through the point cloud and find spheres. You'll see they're colored. They're green, so that means that there were enough points on those spheres that were measured from the point cloud that it could have a very good fit and determine that those are, in fact, 5-inch spheres. And then the software uses those 3 points right there to tie the 2 scans together. The next method that we can do, and each of these have advantages and different uses, but there's been a lot of advancements in this next method that's referred to as cloud-to-cloud. And cloud-to-cloud allows us to just take common geometry, common features of multiple scans, and to fit them all together by comparing the thousands and thousands of points that we have. So in this example, you'll see 4 scans, and what we're concerned about here is seeing overlap from scan to scan. So scan 0 to 1 has enough overlap that the software can compare those two and fit them together, kind of like a jigsaw puzzle. And then we get a registration report that just tells us, you know, these scans were within this many millimeters of each other, and so that's our registration report and how we determine whether or not this was a good registration and a good fit. noise. This is always a question that comes up. It's not hard to recognize that if someone walks in front of your scanner while the scanner is operating, that's probably going to cause problems. And problems is probably too serious of a word for it. Simply because it's a line-of-sight instrument, if someone gets in the way, they're then going to be measuring the points on that person or that car or that dog or whatever is in the line of sight. And generally, it's only a problem if someone or something stands in the way for an extended period of time, because then you're actually blocking your area of interest. So sometimes you'll have to just make people aware that something's going on and they need to kind of stay out of the way. And the one thing about the scanner is everyone finds it fascinating, so everyone wants to have a conversation about it. And usually if you're out scanning, people are going to come up and start that conversation. And so anyway, you'll end up with people in your photographs and in your scan data, but it's okay because we'll just remove those parts as needed. So if it's interfering with our workflow, obviously we'd want to prevent as much of that as possible. But working in the real world, we all know that there are things out of our control. So what do? Here's a screenshot of a point cloud that's been colorized. So on the street, it was a very busy time of day, and you can see plenty of stray points there in the roadway. And also you can see me on the left side there standing near one of the fire hydrants. I got in the way too. So this is not a big deal. Inside the software, they make it very easy to isolate different parts of scans and simply make a selection of the points that you don't want to keep and deleting them out of your data set. So once that happens, just in a few clicks, we get rid of all that information. All right, what are your technical needs for working with point cloud data? As mentioned earlier, we're all inundated with tons of information about technology, and everyone knows that things are growing by leaps and bounds all the time. And thankfully, everything has caught up to the world of point clouds. 2 years ago, to work with point clouds was very difficult. The software just wasn't built to handle the millions to billions of points that we can create with these type of measurement devices. Autodesk has done a fantastic job of integrating point clouds into all their software. We're currently in a release cycle for all the Autodesk users out there. And 2016 software has further integrated point cloud information, making it easier and easier to work with. There's new tools available that allow you to extract some information out of that, like lines and planes. It's becoming easier and easier to work with point clouds. As far as your hardware goes without saying when we all want the fastest hardware we can get, right? Dealing with point cloud data and actually doing the registration and the processing and the colorizing of the point cloud, all of those are very processor intensive, and working with the workstation is an absolute necessity when it comes to dealing with point clouds. If we try to skimp on the hardware, we'll end up pulling our hair out dealing with just waiting and twiddling our thumbs. And I know we all want to be more productive, so I would definitely recommend not cutting any corners when it comes to the hardware that you choose to use with 3D scanning. Maxing out RAM. The files that come out of 3D scanners are large by standards if you're thinking of CAD drawings. So CAD drawings are usually measuring in 10, 20 megabytes maybe when they start to get large. Revit files obviously get larger, but still each file that we're looking at for 3D scanners can range anywhere from 70 megabytes a piece up to 300 and 400 megabytes depending on the density that you choose to scan at. So if you're doing a large job that requires hundreds of scans, you can see how your technical needs will grow considerably. So maxing out RAM, the computer that I use to process data is a laptop, but it's an Intel i7, and I have 32 gigabytes of RAM, and that serves very well. It works very quickly. There's always waiting when dealing with gigabytes worth of files, but it's very dependable. The next part, and probably the most important part of this, is a solid state hard drive. The spinning drives that we've all been used to for years are, were great for storing large amounts of information, but they're not that fast. And your biggest bottleneck that you're going to have when working with point clouds is if you have a slow hard drive and you're having to wait for gigabytes worth of data to come off the drive and go into your memory. Once we have our point clouds registered and we have them ready to go into our CAD software or Revit and then a PDSM suite, whatever we need to use, we have to ask ourselves a question, what do we need to model? The point cloud by itself is incredibly useful. We can measure from any point to point. We have, again, the panoramic photographic images. That in itself is fantastic and changes the way we work and makes our job easier. But it's not a 3D model in the sense of working with solids or Revit families or specific piping information. And so depending on the type of job you have to determine what do you need for modeling. So if we're looking at piping, for instance, we may not need to model an entire facility with every elbow and every reducer and every T. We might just need to get our tie-in points. So we would just choose a software that can help us model that and just get those tie-in points. Maybe we're doing an upfit in some building, and maybe we don't need every detail, but maybe we need a floor plan. So we're going to model the walls and the windows and doors, but we're not necessarily going to model every lighting fixture in there. So we talk a lot about level of detail and then different needs for modeling. The inclination for most is to want a complete 3D model, and the fact is it's very time consuming, and it's an expensive process to have someone else do it, and we all want things modeled in different ways. So there are some considerations in what we do with the cloud after we have it processed. So with that, there are some great pieces of software out there. Specifically, we talk about two of them. ClearEdge 3D makes a software called Edgewise, and Faro has recently purchased Qubit, which is a fantastic piece of software also, and they both accomplish semi-automated or in some cases almost fully automated processing of point cloud data into native 3D models like into Revit. So this screenshot from Edgewise, I'm going to talk about how the software does this and how it affects our workflows. If we wanted to model the structure of this existing facility, the software can look at groups of points and determine what it's looking at and make a best fit guess really at what it is. And then we go through a QA/QC process to determine whether or not the software picked the appropriate part size. So looking here, you can see that the green dots on the left are all the points that I selected to allow the software to do the best fit analysis of that beam. And when it looked at it, it says that it's a W21 by 93. And at this point, I can look at those and determine whether or not I agree. If I already know or if I have some documentation, obviously I could just tell it what size and then do the best fit from there. So we would go through each part of this facility and model parts of the structure. And this software has also come a long way very recently, and we're anticipating their next release where it does automated pattern recognition. So once we get some of the elements of this modeled, it can then go and look at the rest of the point cloud and extract more data, extract more parts out of it, and simplifying our process and speeding it up. Once this is set up in Edgewise, once we have all those parts modeled, whether it's pipes, structures, HVAC, walls, all of those different parts can be exported into native formats like directly for Revit. Here's another example of how it looks and finds pipes. Once we import our point cloud here, the software goes and looks for cylinders. All right, it's so powerful how it can just go and find hundreds and hundreds of pipes, and then we fit them to a standard. So in this case, you'll see that this is a 4-inch pipe. All of the green dots there are all the points that were found in that area, and then the pipe is aligned and then best fit into that space. Once we assign the standards to all the pipes, we can then join them all up and make them complete runs. We can put in the elbows and T's and valves as needed. And then again, we can export that out to Revit. And while we're moving on, if you would please submit in the questions box what software you're working with. I'd like to know just generally what you're spending the majority of your time in. And feel free to put a little bit more information in there if there's a specific application that you're curious about. Here's a screenshot directly out of Revit. You'll see that we have a couple of cross-section lines drawn in there, and we're looking at the point cloud. So when we import a point cloud into Revit, it adjusts our view range so that we're just seeing part of the point cloud data. So with very little input from us, we're already working on our floor plan here. All right, looks like we got a variety of different softwares here. It's good. Thank you guys for submitting those. So what can we do with this point cloud now that it's in Revit? We can use this information as kind of a let's see, like we can just trace over it. We can use it as a reference. All right, so we can just go through the process of determining, let's say we want to model some walls. So we just choose our family, choose how we're going to insert the walls, and then just trace over the point cloud. This is, so 2000, I think it was 14, there was a big leap as far as how we deal with point clouds inside of Revit, and before that, we weren't able to even snap to the point cloud and use it as a reference for nodes and whatnot. So now things are getting a lot better. We're able to snap to points inside of Revit. We're able to detect planes and intersections and things like that. So it's a much simpler process. In this screenshot, you can see where we've started to do some of the modeling. All right, so now the walls have been placed. We've got some doors, some windows, some openings in the walls. All right. The next screenshot here, now we're looking at one of those cross sections. You can see the walls and the point cloud with a clipping plane there. So we're obviously only viewing a small section of the point cloud, and you can see where we've got the joist placed. And so this is the manual way of looking at this, and there's nothing wrong with doing it this way, but we always want to do things faster, right? So I want to take a quick look at a piece of software that's getting ready to be released from Faro and Qubit that's going to speed up the entire process inside of Revit directly. And then from there, we'll start talking about more of the options. I see some people are using Plant 3D here. It has some other questions. So then we'll start to tackle your individual questions after this video. So you can see inside of Revit, instead of manually just tracing over lines, we're able to intelligently extract data. This also takes out some of the questions that go about of how do you determine where you're going to place walls and doors and things. You know, at what point on the point cloud should you be clicking? So here you can see just by picking points from the photographs that came from the scanner, you're able to intelligently place different components. So we're looking at the automatic pattern recognition there. So if we're looking for a beam, if we're looking for different structural elements, the software is able to pick the point cloud that's in that area and extract the most likely family or a type of unit. All right. So I hope that you were able to see, actually see this. I know that sometimes the bandwidth is a little bit of an issue on webinars and whatnot. But if you want to see more of that, that's available on YouTube, and it's Qubit Point Sense for Revit. I'm going to jump out of the PowerPoint presentation here for a second. Okay, so here's a live point cloud, and this is in Autodesk's Recap. So Recap is used for registering point clouds together, and also for viewing and measuring. It's just, in general, it's a great communication tool. We can take our point clouds and upload them to the internet cloud and share that information with a remote office or a client. So I'm going to do a little fly through here. So we can see here's that open spot there in the middle of the floor. So that, no, there's not a hole in the floor. That's just where one of the scan locations were. And that's that small area that wasn't picked up that was directly below the scanner. And so you can see how there's other scan points that are starting to fill in that gap. So from scan to scan, we can fill in those holes. All right, I'm going to come up here, look up at the ceiling, look at this ducting. So we have a nice image here. This scan was done very quickly. It only took about an hour. There were 9 scans. I would actually call this a low resolution scan. But this is still plenty of information for us to model any element that's in this space. I'll pan around here. So you can see the piping here. And you'll probably notice that we don't have the whole pipe scanned, right? We don't need to scan every single inch of a pipe for the software to extract that information or for us to even manually model that. Generally, the softwares only need 20 to 30% of a pipe to actually figure out what the size of it is. So the speed at which we can capture the scan data is phenomenal. You know, just in an hour's time, and I cannot remember the square footage of this building, but you know, it's a nice open space, so that makes it easier for us. But with just 9 scans in about an hour of our time, we've documented this facility, and we would be able to either model this or simply use it as a reference point for a design, and then we could do clash detection on that using a software like Autodesk Navisworks. All right, we talked about the panoramic images. So I'm going to switch over here to this scan, and I'm going to switch over into what's called Real View, and we'll be able to view the panoramic image in full color. All right. So now this is the photographic data, and we can zoom in here. You'll see the closer I get in, you see how it does start to become a little pixelated just because it is a photograph. But because what happened at the same time as the 3D scan, we're still able to take measurements while viewing it in the photographic mode, so I can get an idea. All right. And I have this horrible habit of working in metrics, so I'm going to switch this over since I imagine most everyone here is in the United States. So there we go, 3 foot 7 4/8. So just measuring off of the photograph, and it still is able to read into the point cloud information. So you see we have everything above us. We can jump back out to the 3D view. All right, so we have one attendee here that is using Civil 3D, doing tins and cross sections. One second. So that's definitely something that we can use a terrestrial scanner like the Focus for. And the good thing about the laser scanning in general is that we have a plethora of information, right? We have a full picture, much more complete than just taking a few shots over the ground on a grid. The other side of that, which is a little hard to grasp at times because of the way that we're used to working with our applications, is point cloud data is a little bit too much when we're talking about tins and surfaces in Civil 3D. So what we have to do is we do have to simplify that data to a degree. And generally, what we would do is in Civil 3D, we would create a surface from the entire point cloud. And then from there, we would be able to start extracting points at the necessary features of the land. And then that would build a tin that is, well, more aesthetically pleasing because we're used to dealing with simple contour lines. In addition to that, we can get volumes. So we're able to define an area inside of in this case, we're looking at the scene software from Faro. We're able to essentially pick a bounding box and then determine if we're looking at a pond or if we're looking at a dirt pile. We just pick those points and it builds a mesh, and then it gives us our total volume. This is a very quick way if someone's wanting to verify pond volume before they pack up and take their tractors. Within a few scans, you can cover a very large area, register that in also just a few minutes, and then build this mesh to get your volumes. In the same regard, if we wanted to look at concrete slab flatness, we take these scans and we determine our, what elevation are we going to check our deviation from. So in this map, we have a nice, so the green shows a little bit of a depression. Red is almost right on, so this was based off of a 100-foot datum. We could also export reports from this. So we'd be able to get coordinates for exactly where those depressions are, those high points. And so if you can imagine the usefulness there, just before concrete dries, like getting your scan and determining where your lows and highs are, so you can fix that before you're dry. Can calculate beam deflection, so we fully understand the load. Can do as-built drawing verification. So if we were in a situation where we actually had documentation, many times when we're starting a new project, we just don't have good documentation. But if you did have documentation, then getting scans and comparing that would be a perfect way to verify everything was installed correctly. So I had a question here. Should we wait until 2016 if we were to get the hardware and edgewise software? I might need a little bit more information on that. Hardware and software, well, the hardware requirements are not really changing too much for new versions of Autodesk software. I don't know if I'm answering your question directly. So here's a screenshot of a clash detection. So the point cloud of the existing facility is there in gray. And then the colored parts are the design. So before we get to work in the field, we want to make sure that that's actually going to work. We can see there are a couple of issues with the design. We have one question here about aerial images. Curious what we use to shoot the aerial images. So all of the images that were shown in this webinar were taken directly from the Faro scanner. So they were either screenshots or we were just looking at point clouds there. Going on to the question about for the gentleman that uses Plant 3D, I don't know if you're familiar with Qubit or if you're working on any projects currently with 3D scanning. I'd love to hear if you already have experience with processing data for use in Plant 3D. Qubit has software that automatically extracts the piping and automates the process of placing valves and bends and all of that, and then it's all spec driven based on your settings in Plant 3D. So you would export out whatever spec you were using for Plant 3D and just apply that as you're extracting the information from the point cloud. We're just about out of time here. I have one person requesting to see plan view in Revit. Give me just 1 second. I can open up Revit for us. So the softwares that we've mentioned today have been ClearEdge 3D. They make the software called Edgewise. And the second one is from Faro called Qubit Point Sense. So we'd love to continue the conversation with all of you that are on with us today. If you have more questions, if you're looking to do, if you'd like to have a demo performed and ask some more in-depth questions about the workflow and just what it looks like to work with 3D point cloud data, we'd love to chat with you some more. So this is the same data that we were looking at there in the screenshots. All right. Well, so I think this pretty much closes us up. Again, we'd love to hear, get some feedback from you on what you're looking at with 3D scanning. Feel free to give us a call or visit us at www.tpm.com. I really appreciate you attending.